Good afternoon, ladies and gentlemen. I'm very delighted, and it's a great honor to be among with you today to introduce this high lecture dedicated to a crucial indicator of global warming and essential climate variable, sea level rise, which was possible to measure thanks to 30 years of space-borne measurements. I'm Selma Shershali. I'm the head of Earth Observation Program within CNES. And this lecture in this year is very timely correlated with three major events for space altimetry. First, since August, we are celebrating the 30th birthday of the launch of the first mission TOPEX Poseidon, a fruitful of close cooperation between CNES and NASA. This mission opens 3 decades of successful space altimetry results in Earth science and then allow the development of applications and services. This cooperation was then renewed with the series of operational satellites JASON-1, then JASON-2, and JASON-3, and was extended to NOAA and EUMETSAT, the operational meteorological agencies. The European Union's Copernicus program then ensures the altimeter reference series with the Sentinel-6 satellites developed by the European Space Agency. It brings me to the second event of this year. End of March, the satellite Sentinel-6A Mike Freilich has taken over JC3 as the new altimetry satellite reference. The third event this year will be the launch of a new generation of altimetry mission, the Surface Water Ocean Topography mission, in December. If NASA and CNES, with the help of CSA and UKSA, have decided to make this mission happen, it's in great part thanks to the solid trust we have in our collective capability to handle such innovation and challenges and improving our continuous measurement in the space altimetry. The highlight lecture will show you the exceptional, outstanding results thanks to altimetry measurement and data. Annie and Lee will present this extraordinary adventure and how it may a big breakthrough in our understanding climate change effect in ocean, but how also it opened unexpected doors in different Earth science fields and applications. Let me now introduce our guest stars, the 2 lecturers. Annie Cazenave is an emerita doctor, member of several prestigious science academia worldwide, France, USA, UK, Belgium, and India, and received several science awards, including the prestigious Vetlesen Prize, Columbia University in 2020. She is always advocating the importance of science and is invited in numerous international lectures each year around the world. Dr. Li Fu is an eminent senior research scientist at JPL, member of the US National Academy of Engineering and fellow of the American Geophysical Union and the American Meteorological Society. He received several awards, including the Distinguished Alumni Award in 2017. Annie and Lee were pioneers in the field of ocean since TOPEX Poseidon, and their contribution to international community is really huge. They already collaborated together through different papers and books. So let me now give the floor to Li Fu to introduce this high lecture. Thank you very much.
So bonjour, good day, everyone. It's a great pleasure and a privilege to have this opportunity to speak to this Congress on the 30 years measurement of sea level from space. In my mind is also to commemorate the 30th anniversary of the launch of TOPEX Poseidon. That's basically launched my personal career, and now it's a great opportunity to reflect. And so before Annie tells you about the global warming and the sea level rise or the science, I'd like to take this opportunity to give you some background about the measurement of sea level from altimetry. However, let's start with the greenhouse effect, which causes global warming. So this diagram shows you that about 1/3 of the incoming solar radiation is reflected back to space, leaving 2/3 absorbed by the atmosphere and the surface. However, a small, the fraction of the radiation, infrared radiation of the surface is absorbed by the greenhouse gases like water vapor, carbon dioxide, and radiated back to Earth. So this is an effect of a blanket, keep Earth warm. If without the greenhouse gas, the Earth's surface average temperature would be minus 18 degrees Celsius as opposed to 15. However, too much greenhouse gas makes Earth unbalanced in heat. Then where all this global warming going? It's in the ocean. It's a giant air conditioning of the planet. So 93.4% is an estimate. The majority of the heat goes to the ocean. Without the ocean, an estimate of the temperature of Earth's surface would be a scorching 67 degrees Celsius. Obviously, we cannot live in that kind of a temperature. So it's very important that we keep an eye on the ocean all the time. However, in the past, observing the global ocean used to be taking years to make strenuous, scanty surveys before the space age. For instance, you see the ship tracks, surveying the ocean during the IGY years of 1957 to 58, and took 2 years to sample the Atlantic Ocean. During this time, the ocean changes a lot. So the ocean was never properly sampled in the conventional ways. And observing the ocean from space began in the early 1970s. A revolutionary concept was to observe the sea surface by orbiting radar in space. And a major milestone, of course, was the launch of TOPEX Poseidon. And the 40 years partnership of NASA and the CNES is the reason for launching this landmark mission and its series of follow-on missions, making precise measurement of the sea surface height every 10 days from satellite altimetry since 1992. And the challenge of radar altimetry is accuracy and precision. We have to measure the sea surface height within the few centimeters from an orbiting radar more than 1,000 kilometers above. So over the years, between the launch of the first radar altimeter in the mid-1970s by GEO3 and going to CSAT, GeoSat, ERS, and TOPEX Poseidon all the way to JSON, in these 25 years, the precision, the accuracy improved by 100-fold. So the vertical scale here is logarithmic. And you can see, I put the size of a quarter of the US there for comparison. And now the accuracy is reaching 1 centimeter by JSON 3 and the Sentinel-6. So with all this tremendous record of 30 years, there's numerous fundamental discoveries of the ocean. I don't have the time to go over all of them, but I select a few on my mind as the top to share with you. The first is the robust variability of the ocean circulation. Before launching satellite, we thought the ocean circulation is a very sluggish laminar flow. but not the case. The ocean is full of so-called eddies with a scale about 100 kilometers. That's the analogy of the atmospheric storms, which the spatial scale of the atmosphere storm is 1,000 kilometers, but the ocean is much smaller. So that's why it's almost missed by the shipboard observations. With the CSAT, the top figure shows you in 1 month, we're already able to map the pattern of the ocean variability or the ocean storms. The lower one is the most recent record based on 30 years observation. As you can see, the pattern of the ocean variability is much better revealed. On larger scale, for instance, over the entire basin of Pacific, the sea surface height is sloshing back, with a change of 1/3 of a meter. That's a huge change, creating El Nino and La Nina. That's the seasonal to interannual climate variability. And in 1997, when the biggest El Nino taking place, Topex Poseidon made the El Nino a household name around the world because the devastating weather disturbances, happening all over the world. And another thing, interestingly, is tides. It's an oldest pursuit of human mind. People thousands of years ago wondering about the ocean tides. And Topex Poseidon was specifically designed to map tides because we have to remove tides in order to study the remaining signals, which is ocean circulation. Here, instead of showing you the familiar pattern of the large tides, the M2, S2 tides, I choose to show you a very small, rarely known tides called degree 3 tides. We all know that the gravitational potential of tides is symmetric, but there's slight variation, asymmetric component, causing this degree 3 tides, very small, although not really having practical applications. But this esoteric finding, I think, is a testimony of the profound impact of a measurement, the massive 30-year database of altimetry with extraordinary precision and coherency reveal this small change of the ocean. The next one I want to introduce to you is the so-called internal tides. It's a very small amplitude sea surface variation, about 2 centimeters. On the left panel, you see all those wiggles. It's only 2 centimeters. Before the launch of Topex Poseidon, nobody even dreamed that you can see such small-scale tides. Although surface elevation is small, but it's a reflection of the huge oscillation of the internal density field of the ocean resulting from the tides. So this is the internal tides, and it's closely related to another significant finding of Topex Poseidon is the dissipation of tides. The lower right figure shows you the pattern of the dissipation to people's astonishment, as opposed to the conventional notion. The tidal dissipation usually occurs, most of them occurs at the shelf seas. In fact, that 1/3 of the tidal dissipation takes place in the deep ocean. That's a very important finding because that's the source of a mixing of ocean waters and correlated with internal tides showing at the upper graph. So the correlation of the generation of internal tides with ocean dissipation driving the mixing of the deep ocean, which is the driver of the general circulation of the ocean. And also seafloor topography, to first order, the shape of the sea surface reflect the gravity anomaly caused by the seafloor topography. So this is the first objectively determined the seafloor topography published in 1997, and is based on well-sampled consistent spaceborne observations. And finally, the topic of today's talk, global sea level rise. That's yet another surprise, because when we launched TOPEX Poseidon, although that at the time was the most precise altimetry mission, the requirement for orbit error is 10 centimeters. So now we have the precision about 1 meter, 100 times better than the original requirement. The reason we can achieve this is an extraordinary collaboration of oceanographers, geodesists, electrical engineers, so that now we actually have the basis of the modern sea level change. In fact, has an increasing trend from 2 millimeter per year when TOPEX was launched to 3 millimeter per year when JSON 1 was launched, then to today's 4 millimeter per year. So I'd like to switch the floor to Andy to tell you about the science about the sea level rise and climate change.
Thank you very much. So the two main causes of present-day sea level rise are ocean warming and its consequence, ocean thermal expansion, and land ice melt. And on the left-hand side of the figure, you can see the ocean heat content increase during the last few decades. The ocean is not only the main reservoir of heat of the climate system, but the heat content is increasing, as you can see. On the right-hand side of this figure, you can see an example of glacier retreat. Here it is glaciers in the Swiss Alps. You know that the world glaciers are melting, retreating, and the ice sheet Greenland and Antarctica are also losing mass. And this land ice melt is the second main cause of present-day sea level rise. We have at our disposal different observing systems that allow us to quantify the different contributions to present-day sea level rise. For example, the Argo network of automatic profiling floats that measure the ocean temperature from the surface down to 2,000 meters in the ocean allow us to estimate ocean warming or ocean thermal expansion. And the GRAY space mission, launched for 20 years now, measure mass redistribution in the Earth system and in particular ice mass loss from Greenland, Antarctica, and the glaciers. So on this figure, you can see on the bottom part the different contributions to sea level rise, land ice melt, ocean warming, and their sum is a red curve that is compared to the altimetry-based sea level rise, and you can see that the two curves agree very well. So assessment of closure of the sea level budget is important, for example, to detect acceleration in one or several components, to detect, for example, tipping points, that is irreversible change of, for example, Greenland or the Antarctica melting. It is also important to cross-validate the different observing systems that are involved in this global mean sea level budget assessment. And overall, it is important for validate the climate models that are developed to simulate future change. We have seen that sea level is rising, but it's not only rising, but it is accelerating. In fact, Lee commented that. For example, for the decade 2001 to 2001 to 2010, the rate was close to 3 millimeters per year, and the following decades, it is larger than 4 millimeters per year. And we know now that this acceleration is mostly due to accelerated ice sheet melting. And this is illustrated on this figure, where you can see here, as a function of time, since the beginning of the 90s, the Greenland ice sheet mass loss. You see a clear acceleration, and over this 30-year period, the Greenland ice sheet lost about 5,000 billion tons of ice, or gigaton of ice, which is absolutely huge. And we have the same phenomenon in Antarctica. This is illustrated on this figure. I forgot to say for Greenland, but this is the same for Antarctica, that these measurements are based on different space techniques, in particular satellite altimetry, but also space gravimetry. So in Antarctica, in particular Western Antarctica, lost during the last 30 years about 3,000 gigatons of ice. If in Greenland, part of this ice loss is due to surface melting in summer, this is not at all the case in Antarctica. This ice mass loss is mostly due to dynamical instabilities at the periphery of the ice sheet. This is illustrated on the right-hand part of this figure. So warm waters melt from below the ice shelves that buttress the coastal glaciers. So when the ice shelf melts, finally it breaks, and the upstream glaciers become unstable, and it flows very rapidly into the ocean. So this dynamical instability is the main cause of ice sheet mass loss in Antarctica, in particular in the western part of Antarctica. The glaciologists are looking at these particular glaciers located in West Antarctica, the twice glaciers, which is currently disaggregating. You have probably heard in the media or seen on internet that these huge glaciers is currently disaggregating. And if it totally collapses, it will cause about 65 centimeters of sea level rise alone. So we are looking at these particular glaciers, but not only that one, all others in Western Antarctica and around Greenland. On this figure, you can see a projection of future sea level rise for the future decade. This is based on the last IPCC report published last year. And the curve at the bottom shows the expected or simulated sea level rise for different warming scenarios. In the case of what we call the business as usual greenhouse gases emission, by 2100, sea level could be higher than in 1950 by about 1 meter. But if there is irreversible ice sheet melting from Greenland and Antarctica, as it is currently occurring, this sea level rise or sea level elevation by 2100 could be even much larger than 1 meter, between 1.5 and 2 meters. And obviously, this will not stop by 2100, but it will continue for several centuries. So, because sea level is an integrator of change in all components of the climate system, it is now it is part of the 7 main indicators of global climate change, as defined by the World Meteorological Organization. And this is for this reason it is very important to continuously monitor sea level using space technique, in particular satellite altimetry. The World Meteorological Organization and the Global Climate Observing System, GCOS, not only recommend to monitor individual climate parameters, but also to look now at global cycles. For example, the global carbon cycle, the global water cycle, and the global energy cycle. And satellite altimetry is also now contributing to this important problem. In measuring what we call the Earth energy imbalance, from which we can deduce one of the main parameters or key parameters in climate science, which is the Earth climate sensitivity. So what is climate sensitivity? It is the average change in global Earth temperature surface temperature, in response to radiative forcing, and typically a doubling of CO2 concentration in the atmosphere. So this radiative forcing cause a difference between the incoming radiation to the Earth and the outgoing energy to space. This is what we call the Earth energy imbalance. So with satellite altimetry, we can now measure this imbalance. Classically, this energy imbalance has been measured during the, let's say, the last 2 decades by instrument on board NASA satellites. This is the CERES project, by looking at the difference between the incoming radiation to the Earth and the outgoing radiation out to space. But now, with satellite altimetry, exactly with the altimetry-based sea level corrected for mass change, which is a measure of the total oceanic content, we have an estimate of this energy imbalance from which we can deduce the climate sensitivity. And the result indicates that the climate sensitivity or the temperature of the Earth when a doubling of the CO2 in the atmosphere will be reached will be 3.5 degrees. And this is one of the most precise measurements of the Earth's energy, current Earth's energy imbalance. We have seen that sea level is rising, it is accelerating, but this rise is not uniform. And this has been discovered, obviously, with the global coverage of satellite altimetry. And this is illustrated on this figure. Here we have removed the global mean trend of 3.5, 3.3 millimeter per year. And the red and the yellow and red region correspond to regions where the rate of rise is much larger than the global mean, can be up to twice the global mean. And this is the Indian Ocean, the Western Tropical Pacific with many low highlands, atolls, etc., the North Pacific, Southern Pacific. So it is also an important measure. In some regions, since the beginning of high precision altimetry, the mean elevation reached 25 centimeters compared to the global mean of about 10 centimeters. So now I move to a new challenge that we have, which is the measurement of coastal sea level rise. And until very recently, we were unable to answer the question, does sea level at the coast rise at the same rate as the open ocean? Why? This is because at the coast, sea level is the sum of the global mean rise that we have seen, which is acceleration, plus the regional variability, plus small-scale coastal processes, for example, shelf currents, small-scale eddies, trend in waves, or freshwater input from river runoff in estuaries and delta. And these small-scale coastal processes vary from one place to another, and they are very poorly known or even unknown. So we are expecting that at the coast, sea level will rise differently from the open ocean. And it is very important, obviously, to know how much sea level is rising in the coastal zone, which are the home of more than 10% of the world population, and which are suffering a lot of stress that I will not comment, but among them, sea level rise, with a lot of negative coastal impacts. Classical altimetry was optimized to, as Lee explained, to measure the open change or the topography of the open ocean. And in a band of about 10 to 15 kilometers around the world coastline, there are measurements, but they are of poor quality, and up to now they have not been interpreted. And the reason is because when the satellite approaches the coast, the radar echo, which is or the surface illuminated by the radar, is several kilometers in diameter, and the radar echo is perturbed by reflection from land. However, with specific reprocessing, it is now possible to approach the coast and to have an estimate of the rate of sea level rise in the world coastline. And this is illustrated on here 3 examples. So on the left-hand side, you have geographical maps. The black straight line shows the satellite track. And on the right, you have the rate of sea level rise or sea level trends over the last 2 decades computed as a function of distance to the coast. So the coast is on the left, and the open ocean is on the right. In the top example, which is a case along the coast of China, you see that the rate of sea level rise at the coast is similar as the open ocean. Okay. But the middle example, which is the case in the Mediterranean Sea, we see a clear increase in the last few kilometers to the coast. So here we have a case where the rate of sea level rise at the coast is faster or larger than in the open ocean. And the third example in the bottom, in the Caribbean region, here we have an example where the rate is smaller than in the open ocean. So we are now able to estimate this rate of sea level rise almost everywhere along the world coastline. And here I show you a map that of what we call virtual coastal altimetry station, where we are able to estimate the rate of sea level rise on the long term. These are the green dots. And we have superimposed the current tide gauge network, which is usually used to estimate sea level rise or sea level change at the coast. These are the red, white squares. And you can see that if, obviously, in North America and Europe, the coverage is very large, but in other regions of the world, for example, Africa, there is absolutely almost nothing. Same in South America, India, etc. Now, I move to the last part of my presentation. And we will see that satellite altimetry also contribute routinely now for more than 20 years to study the global water cycle. So satellite altimetry is used to measure water level of lake and rivers, and this is done using all satellite mission, altimetry mission, since 2 decades. And here you have I show you an example. This is a Tonle Sap Lake in Cambodia. And you can see on this figure the seasonal variation of the lake water level as a function of time since 1993, with years where the level is high and years where the water level or the lake level is smaller. And this is correlated with El Niño and La Niña events. And this is very important to have this kind of measurement because the lake is connected to the Mekong River, and using this data for example, together with hydrological models, help in obviously observing what is going on, but also predicting, forecasting future change. So why is this important to have this data from space? If this is illustrated on this figure that shows you the global runoff data center, which is the current state of water level and discharge data available at the date of 9 September this year, so just a few days ago. And the color of the dots indicates the last available data, the year of the last available data. You can see that, for example, in Africa, we have no data beyond 1985 or 1995. And this is the case in many other regions in the world. And satellite altimetry in some region complements the in situ network, but in some region like the Congo Basin, where we have absolutely no in situ gauge or station, it provides us invaluable data of river water level. So here you can see the white square represent virtual station based on altimetry data, and these virtual stations are defined as the intersection of the satellite track with the river, as you can see on the bottom left of this figure. And this animation here shows you high and low water level in the Congo Basin, monitored by satellite altimetry with different missions. And the red color shows the region and period of high waters, and the blue and the green color show period and region of low waters. And there are many applications of this. For example, obviously, water resource management, crop irrigation, and navigation, etc. So now I come to my last slide. I would like to show you another example of the monitoring of river levels. And here, this is over the Indus River. This illustrates the recent floods in Pakistan that affected this region during summer this year. So on the left, you can see the high and low river level of the Indus River Basin. On the left for year 2021, and on the right for this year 2022. So we are now in July and August, and you see that many parts of this basin are affected by very high water level, and this which caused floods all over Pakistan. So I think I stop here, and it's to you again.
So Annie has told you a great story about global warming, ocean heat, and the impact on sea level, water cycle. So it's imperative for us to have the ability to assess the ocean's capacity continuing absorbing heat, as well as the ability to calculate the water budget so that we can manage our water resources, and also assess the coastal impact of sea level rise. So now the topic is what do we do next? So the conventional altimeter provide all the evidence, but doesn't have enough spatial resolution allow us to do all those quantitative calculations. So SWOT will address the key elements Andy already addressed: the energy, water cycle. This is the source of climate change and its consequences, including coastal sea level rise. So surface water, ocean topography, SWOT, as Selma already introduced to you, is a Pathfinder mission using new technology to measure the elevation of water on Earth with unprecedented resolution. It's 1,000 times higher than conventional altimetry and the coverage. So similarly, mapping between 78 degrees north and south every 21 days. So water elevation on land provides water storage and river discharge. So this gives us water budget and cycling. And the water elevation over the ocean topography, we already discussed that a lot, provide the ocean current and speed and direction. So that drives ocean flux of heat and carbon. So what is SWOT? SWOT is an interferometry radar system. The key technique is to use a 10-meter mast to separate two imaging radar using the slight difference in phase between the two antennas to determine the direction of the radar waves. So in addition to nadir, now we can map ocean topography off nadir so produce two-dimensional maps of the ocean surface as opposed to conventional altimeter, which gives you a one-dimensional profile. So this one just shows you the animation, how SWOT is measuring ocean topography in south of Florida, the Florida current, now over the land, mapping all the water bodies of Florida, then back to the ocean to catch the Gulf Stream. So this will weave the ocean every 21 days, leaving no gaps. So some technical challenges. This is a Pathfinder mission, I said, because never done before in space. In order to produce the precise phase information, we'll have to maintain the stability of the 10-meter mast to within a few microns, less than the thickness of human hair. We also have to maintain the orientation of the spacecraft in orbit to within 1/10 of a degree, and knowing the orientation all the time to 1/100th of a degree. And all this mapping create a huge amount of data. Is 1 terabyte instead of a gigabyte, so it's 1,000 times that of a conventional altimeter. And in the open ocean, the upper diagram shows you the eddies and fronts, which is the analogy of an atmospheric thunderstorm squall lines. When the thunderstorm passing through, you feel the rapid drop of temperature because of the vertical motion of the air. In the ocean, all these eddies and fronts provide the mechanism to do vertical motion. The lower one shows you a transect of this that transports carbon dioxide and the heat from the upper ocean to the deep ocean so that we can assess the ocean's capacity to absorbing carbon and heat to evaluate the future course of climate change. And on land, we have all this high resolution of measurement of rivers and lakes. So the coverage progressed from 15%, the current capability, to over 90%. So in the past, only very large lakes like Lake Garda in Italy and Lake Tahoe, all these huge lakes, only those lakes can be observed by a conventional altimeter. Now SWOT can observe the elevation of a small pond, only a few acres. And also the impact of sea level rise, of course, that is felt at the world's coastlines. Just to give you an example, a few years ago, Hurricane Sandy created a lot of damage to New York City. But because of the global sea level rise, it produced additional $2 billion of damages. So we can actually calculate the cost of sea level rise to a city like New York. And also, the lower left shows you the entrance of the Mississippi into the Gulf of Mexico. If sea level rise can cause diversion of rivers like this, create massive floods. And also the saltwater intrusion contaminating the water table, all that can be assessed by the high resolution elevation data off coast from SWOT. So the status of this mission, from the original concept to the build of hardware is, I would say, is 20 years in the making. We made the original presentation of the concept 20 years ago in Japan during IUGG conference. Now we're finally in the state to launch this in 2 months. So it's an international mission, primary contributions from CNES and NASA. Now we have enlisted contributions from Canadian Space Agency as well as the UK Space Agency. It's a 4-partner mission. The payload module, the instrument package of SWOT was completed by JPL during the pandemic and integrated to the satellite bus in France this year and fully tested by CNES and Thales teams. So this fully integrated satellite will be transported back to US for launch by the Vandenberg Space Force Base in California by SpaceX Falcon 9 rocket in December this year. And the international team of science and applications waiting for many years are ready for this exciting mission. So I would like to end this presentation with this positive note. Let's go for SWOT. Thank you.
Thank you very much to Annie and Lee for this very excellent overview of the achievement and the preparation of the future. We have now some questions that could be perhaps addressed in the few minutes latest. So the first questions was what are the key reasons for the decrease in sea level rise? Are any of these level decrease drivers scalable?
Decrease in sea level rise?
Yeah, what are the key reasons? I think they misunderstood that the sea level is rising. So perhaps if you could comment on this. And will we lose island nations like the Maldives in the next 50, 100 years?
Okay. I don't think I am able to answer the first question because sea level is not decreasing. It's in terms of global mean, it's rising. It is true that because of the regional variability, that in some regions, for example, south of Greenland, the rate is smaller than the global mean, but it's not decreasing. It's still rising, but slower. The question about permanent flooding of some region in the world, yes, I don't know the time scale, but definitely because sea level will continue to rise well beyond 2100. For example, if we stop greenhouse gases emission tomorrow, sea level will continue to rise for several centuries, and there are two reasons for that. The first reason is the heat that is already accumulated in the ocean, as Lee showed. And the second reason is the lifetime of CO2 already stored in the atmosphere, and which is several centuries, again, even millennia. So obviously, if we stop greenhouse gases emissions, the rate of sea level rise in the future will be slower than if we continue to emit, for example, at the current rate. But sea level rise is a slow process that will continue for a very long time.
Unfortunately.
Yes,
So,
of course.
Another question, can ocean level data help in early displacement of people affected? For example, Pakistan people could have been displaced earlier.
Can you answer that? No, it's for you. we have.
This is on. Okay. The current generation of the altimetry, the constellation of half dozen altimeters, provide data which is available on a daily basis. So those data are already adequate to give you information about the floods and also sea level rise. And however, the mission I talked about, the SWOT, will produce even higher resolution so that you can actually calculate the water budget over any river basin. And so those data will be extremely useful for water managers to make a projection of water resources. So our hope is that after the initial examination of this challenging Pathfinder mission, the first kind of data, it's going to take a while for the engineers to weed out any potential glitches. So the data will be available not as fast as JSON or Sentinel-6. We're hoping after half a year or 8 months, then the data fully validated, it will be made available to the public in very short latency in a few days. So data will be useful for water resource management and the prediction of floods and droughts.
Thank you very much, Lee. There are many questions related to costs. As we see, there are very complex areas, Annie, as you mentioned. And the question is, how can the sea level change differently close to cost or far away from cost every year? wouldn't that lead to a steadily increasing unbalance? This is really a critical question, I think, due to the complex process within costs. But the
you mean
costs.
cost line?
Yeah, cost line, yeah.
Yes. So can you repeat the question? Sorry.
How can the sea level change differently close to the cost?
Ah, yes, it's because I explained at the coast, the sea level is the sum of the global mean rise plus the regional variability, plus some coastal processes, small-scale coastal processes that are very poorly known, and the problem is that they can be different from one place to another. And we are, it's a new research area, but now with space data, with altimetry data, we are discovering that at some places, at some coast, sea level can rise faster or slower than in the open ocean. We are just starting this emerging research area. We still don't understand exactly. We are not still able to explain which process is causing what we observe. But we are working hard, and we hope that soon we will be able to understand. And this is very important for projection, for example, because it's important to project how much sea level will rise in terms of global mean in the coming decades. But what people want to know is where, at my place, how much sea level will rise at my own place, and we are not yet there, but we hope soon.
Yeah, thank you very much, Anya. I think it's an important message to say that we don't understand everything at this stage, given the fact that the satellite ultimate measurements provide really a real good indicator with the accuracy measurement. But there are many other research areas that have to be investigated, and I think the close cooperation between science community and the space agencies will lead us also to prepare the future generation of mission, not only altimetry due to the complexity of the costs processes, and there are much more work to do for the future for those complex research areas. We agree.
If I can add something, we are expecting much from SWOT, because so far with classical altimetry we have measurement along the tracks, but the distance between two tracks can be several hundred kilometers. But with SWOT, maybe you can comment on that, SWOT for measuring sea level in coastal areas.
Yeah, absolutely. The sea level rise, there's no question, is rising. You know, the 1/3 of a meter since Industrial Revolution, and but the impact, of course, felt around the world's coastlines, and there's variations, like Annie pointed out. In some places more, some places less, but the impact of sea level rise in enhancing storm surge. You know, the example I gave you about Hurricane Sandy is a good one. You know, we can actually place a cost of lives and property from the extra sea level rise, raising the base of storm surge. And so SWOT data off coast will have a resolution on the order of 50 meters. So instead of have a 1 kilometer resolution, but all these tides and the storm surge would need a higher resolution. So we're hoping that the SWOT data will revolutionize coastal models for storm surge, river diversion, even saltwater intrusion, all these impacts on daily lives.
Thank you very much, Lee. Perhaps 2 more questions to end this session. So, Annie, for you, what will be the maximum sea level rise in meters be if all ice on Earth is gone? We are not hoping this.
Oh, okay. I can answer the question. If Greenland is totally melted, it will be 7 meters of sea level rise. West Antarctica 5 meters, and East Antarctica 55 meters. But forget East Antarctica, because it's not predicted that it will change in the coming decades or even centuries. But West Antarctica is really a region where glaciologists are looking very carefully because, as we have seen in the examples, there are many large glaciers that are losing mass and there may be some runaway melting in the future. And this is, for West Antarctica, it could be 5 meters of sea level rise. Not tomorrow, but in a few centuries.
Perhaps to end on a positive point and sense, how do we encourage the young generation to contribute to reducing the impact of climate change on one hand, and on the other hand, you are really exemplary for the young generation to motivate them to engage within this science and research activities related to climate change and to the climate change impacts. Please.
Well, you know, the previous generations created this problem. And the Industrial Revolution drastically improved people's lifestyle. So today, the climate change and all the devastating consequences one can view, that's the price the new generation is paying. However, they do enjoy the modern lifestyle. And so I personally think that the engineers improve the lifestyle of Industrial Revolution. Now the consequences should also be addressed by engineers. Of course, the science is important. You establish the evidence, but what are we going to do about it? Okay. On the one hand, we need a higher resolution measurement so that we can more accurately project future climate change, so that the next generation will have a better database to evaluate strategies of mitigation and also adaptation. So I think that the future is in the hands of the next generation. And what we have done so far is hopefully we have built enough science to understand, to project the future course of action. But I really think that the future engineers, the challenge for them is how to protect life on Earth.
Thank you very much, Lee. Thank you very much, Annie. I would like to request from the audience to give a strong applaud to this high lecture, which ends our session. So thank you very much, Lee. This is really an honor to have you today with us. Thank you very much.